Hi, everyone. Welcome to the Waterloo Institute for Artificial Intelligence seminar series, our third talk of the post-COVID or during COVID era. So today we're happy to have Dr. Emtiyaz Khan from the RIKEN Center for Advanced Intelligence Project in Japan. He's going to talk to us about some fascinating work in using Bayesian principles for machine learning. And he has kind of broad set of research in this area, which he's going to tell us about. He is a team leader at the RIKEN Center for AI in Tokyo. And he leads the Approximate Bayesian Inference Team. He's also a visiting professor at the Tokyo University of Agriculture and Technology, and he's been a researcher at EPFL in France and did his PhD in UBC. So he does algorithms that connect Bayesian methods and fundamental machine learning principles, which are something we really need in a lot of these challenging days with interesting data sets. So let's have a great discussion while he's going, and enjoy the talk.
Thanks for the introduction. I'm very happy to be here and be able to, connect with you virtually. And I know that, we are going through crazy times right now, and I appreciate that you take time and you're still here attending this talk. So thanks for that. So I'll be talking about Bayesian principles for learning machine, and my hope is that I can somehow summarize some of the work that we have done in the last 4 or 5 years and get you excited about Bayesian principles for learning machine. Okay, so I will start with a little bit of big picture to give you the problem that most of the machine learning people are interested in. Is this big question of how can we design an AI that learns like us, like humans, like animals, and like other living beings. And when I say learning like us, what I mean is to be able to learn and adopt quickly throughout our lives. Okay, so I just wanted to start with an example of what I mean by this kind of quick learning and adaptation throughout the life. I show you a video of my daughter here. Can you see my cursor, by the way, Mark?
Yes.
Okay, so this is a video of my daughter, and this is from when she was 6 months old, and she's trying to learn about ukulele. And as you can see that she's trying to, touch around her and collect some observation about the world and try to figure out what she likes and doesn't like sheets she's not very fond of. And slowly she's figuring out that she likes the ukulele, the sound that comes out. So when I say machines that can learn like human, this is what I mean, is that you're collecting observations slowly about the world and figuring out what you like and not like. So we all do this type of things, and we don't quite stop at this place. We if we continue to see data and collect observation, collect experiences about the world, we converge. So here, 6 months after, my daughter has figured that what she wants to do is to strum this ukulele and only get the sound out. So she's not now randomly touching everywhere, but she has learned something about the world, and she's collecting now the experience that she most likes. So this is an amazing thing about human learning, that we sequentially collect observations, collect experiences about the world, and learn some interesting facts about the world. But we don't quite stop here if we given more time. So this is 2 months after. Now she has moved on to a guitar world, where she's using her past experiences to learn new skills, like creating the same sound from guitar. And guitar is a little bit of bigger instrument, but still she's able to get what she wants. So when I say we are interested in designing machines that can learn like us, what I mean is that the human learning is very different from how machine learning is done right now. And I want the machine learning to be done a little bit more like human learning. So human learning is more throughout your life, and it happens in small chunks of interaction in the world. So as we live our day-to-day life, we keep learning throughout our life. And even if the world around us is changing, we can quickly adapt to it. In machine learning, especially in deep learning, the scenarios is quite different. Here we assume that all of the data that we are interested in learning about, it's all available at once, and it's really, really large. And it sort of comes from a stationary world where things don't change. So once we have all this data in hand, we have everything that we want to learn about the world. And my goal in my research has been in putting these two kind of learning, learning mechanisms together. So trying to reduce the gap between human learning and deep learning. And there are two different kinds of learning. And when I say I want to reduce the gap between the two, I really mean that I want the behavior of human learning, the way we learn, should to go in deep learning, and maybe deep learning and machine learning can benefit from the type of behavior that we have in human learning. So when we talk about closing the gap between these two different kinds of learning paradigms, I turn to Bayesian principles because previously many researchers have argued and shown that Bayesian principles can actually explain this type of human learning, where you see slowly small chunks of data and you update your belief to come up with a distribution that sort of contains all the information that you've seen in the past. But what I have been doing in past few years is that I've been looking into how these Bayesian principles can also explain many machine learning, deep learning algorithms. So this talk is more on this side, and the hope is that when we can have the same set of principles to explain human type of learning and deep learning and other machine learning, then we have a common set of principles that allows us to design algorithms that can learn like humans. So that's the big picture. So what today's talk is going to be is I'm going to explain some of the Bayesian principles that I have worked on, that I have found useful for designing learning machines. And I basically focus more on this human-like learning, so like having this lifelong learning, incremental learning, and how to incorporate those behaviors in the machine. What I will try to convince you in the first part of the talk is that Bayesian principles are almost as absolutely essential for having this kind of learning behavior in machine. But the problem is that it is computationally infeasible. Okay, so this kind of puts us to trying to come up with new principles that will help us make this Bayesian principle be feasible for machine learning. Okay, so I'll first talk about the first principle that has to do something with the principle of estimation. And this is really an algorithm Bayesian learning rule that unifies many machine learning algorithms. And I'll show an application on uncertainty estimation. Okay, what we will see that this learning rule is good. It gives you some kind of approximation to the posterior distribution, some kind of Bayesian principle, but it's not enough. So we'll turn into the second principle, and this is really new work that we have just kind of started working on for past 2 years. And this principle is, I call this Bayes dual, it's sort of exploitation principle. And the hope here is that some kind of dual representation that can be extracted from this learning rule, and that can be used to do some kind of knowledge transfer. And I'll give an application of continual learning of deep network. And then I'll close the talk with some discussion about how these two principles can actually lead to more human-like learning in machines. And the disclaimer of my talk is that I'm really focusing on the concept and not going into the details, so I apologize for that, but this is like a preview talk where I introduce these concepts and hopefully motivate you that Bayesian principles are essential for human-like learning. Okay, so I will start with the first part. And my hope is that after every part, I'll take a break, and then we can have some discussion, 1 or 2 questions, if somebody has, and otherwise I'll just continue in the usual way. Okay, so let's go to the first part. Bayesian principles are essential for human-like learning, but they're invisible. Okay, so let's first start with what people do in the non-Bayesian world. So this is in deep learning world. People use these kind of frequentist ideas, empirical risk minimization, maximum likelihood principle. Essentially, you come up with a loss on a data that you observe, and then you have some model with some parameter, I call theta in this, and you try to minimize the loss, and that'll give you a network or a model to explain the data. Right? So just be a little bit more specific about it. You have a deep network, you have some output, you have some inputs, and you're trying to explain the outputs using this deep network, and you have some squared loss, maybe for regression. You add a regularizer, and then you try to minimize this thing. And to minimize, you can use something like a stochastic gradient descent, where you have the gradient and you have a Hessian preconditioner, and then you take a step to update the parameter. And in the end, you will have one model. So you will have one theta that explains the data. Now, this kind of thing works quite well. It's very, very successful. It's well accepted, and it's quite nice. But this type of deep learning is not really, human-like learning. So, for example, can you extend this to a scenario where you have to do lifelong learning? So you see that the algorithm that I described in the previous slide, it basically assumes that all of the data is at one place, and then you can randomly select these subsets of data and update the network using the stochastic gradient method. But what we want is not having all the data at once. Like humans, we don't have all the data at once. We learn every day. We see different things every day. So a more reasonable setting is something like, so this is just one type of lifelong learning. So they call it continual learning. For example, it comes from this paper, where you see a part of the data at one time. So you're given, let's say, dogs and cats out of all these ImageNet classes. And you have to now update your network only on these classes. So you don't see random samples anymore. And then once you update the network, then you move on to see different other classes like lions and tigers, and you'll never see dogs and cats, right? So you see that you're not seeing all data again, and you can't store them completely. So you have to deal with a small chunk of the data. So it's more like human learning, and keep updating things. What people have found that if you actually run standard deep learning methods on these kind of scenarios, they forget the past data. So when you see lion and tiger, it happens that the past categories that you have seen, you might not be able to predict them well. Okay, so that's an issue. So this is kind of a problem, and I want to illustrate, give you intuition on why this lifelong learning, like when you see parts of the data sequentially one by one, why does training becomes difficult? And that will form the main problem of this talk, okay? So to give you that intuition, let me start with a very, very simple example. Here, it's a classification problem. You have one class here, you have another class here. And then I ask you a question, which line here, which classifier is a better classifier? Now, both classifier give you 0 training error, so they look quite good. But if you're a machine learning person, you'll say, well, I should probably pick the blue line because the margin is somehow wider and it gives me more room for making the error. But the issue is that for lifelong learning setting, like you don't know what you're going to see next. So the difficulty is that you cannot really say right now what is the best line, right? It really depends on what happens next, and you don't know what happens next. So suppose the next time instant I got the second set of data and I got it to be here and here, right? So you see now that this thing is misclassified by this blue example, a blue line. Now this seems like a contrived example where I made this situation up, But really, when you are in this situation and you're thinking about lifelong learning, it's like you are young and naive and you don't know what's going to happen. And then you make a decision. You chose blue line instead of red line. And then you pay for it at the later stage because you didn't really know what lies in the future, right? So the main challenge here is like, it's a very, very simple idea that if you made a decision in the past and the future doesn't comply with it, then the past can actually hurt you, you know. And this is the difficulty that if you, like in deep learning, you pick one line, and whenever you make the decision, you've actually, open yourself to failures like this. So how does Bayesian principle actually solve this problem? So the main idea with Bayesian principles is that you want to keep your options open. Okay, so it's very vague term, but essentially in mathematical terms, you can write this as Bayes' rule. So instead of having just one model, you want to have a probability distribution over the model, and it's updated using Bayes' rule. Math is less important. Just think of it like you have a distribution in the end after seeing this data that I have denoted by D1. Okay, so the distribution might look like this. So you can see what I have done here is that instead of having just one line, I have kept many models around and I have assigned them weights, and these weights are assigned according to this probability, right? It's saying this one is the best one, but this one is also not a bad one. It's still included, even though the weight given to it is quite low, right? So the first idea is that by defining a distribution, you're keeping your options open, okay? And then when you see the next set of data, now you can update your belief. So you want to revise your options given new evidence. And the way that you do it is that you repeat Bayes' rule again. So you take this posterior, you plug it in the prior, and then you simply compute the new posterior given both the data sets, so D2 and D1, right? And if you do that, what it'll tell you is that, well, now this line looks more plausible and those lines look less plausible. Okay, so I've kind of hand-made these figures, but I hope that you see the point that you go from, you revise your beliefs and you only be certain when the evidence really supports that certainty. So this idea is actually not new. It's really used in many fields, like in sequential decision making, online learning, and game theory. And it comes under many different names like uncertainty or randomization. And the main idea is just kind of not to commit too quickly. Right? So you want to keep your options open, and you want to shrink your options as you see more evidence. And the rate at which you shrink is somehow dictated by this Bayes rule or something that looks like it. Okay? But the issue here, as you can see, that you have to look at many possibilities. So you have to have many theta. In this case, when theta is continuous, it's infinite. And you have to have probability over all possible theta that can happen. Right? So the computation is infeasible. In technical terms, it's just the difficulty is computing this integral, but let's not get into that. The main problem is that computing the posterior distribution is difficult. Okay, so I hope that this is convincing you to some extent that if you want to do this kind of sequential learning, human-like learning, then you want to keep your option open when you haven't seen all the data. So in the beginning, you've seen very few classes. You want your posterior distribution to be very broad so that you can adjust it later on. But if you do deep learning type of update, it only gives you one model, one theta. It's not a distribution, so you can fail quite easily in the future. And that's the reason why you have this kind of forgetting. Okay, so Bayes is essential, but this idea is infeasible because you have to maintain this posterior distribution. So I want to now in the next part introduce a principle that's going to approximate this distribution, and then we'll see how to make this more scalable and make it more accurate. Okay, so this completes the first part. Are there any questions?
I don't see any yet on the system, so I'm just going to remind people again, if you do have a question along the way, you can type it in and then we can have it ready. And then if these inter-reg parts, Emti can answer them, we can discuss it.
Okay, great. Is my call quality good?
Yeah, seems great.
Okay, that's awesome.
Perfect.
Okay, so I will continue with this. So let's go to the next part where I'm going to introduce you Bayesian learning rule, the first principle, and I'm gonna go over this very quickly because this is just kind of the first part of the more important principle later on. But my hope is to show that Bayesian principle also explains a variety of learning algorithms. And then once we have put all learning algorithms at this, at the same platform with the same principle, then we can try to kind of combine them and use these Bayesian ideas in those deep learning algorithms, for example. Okay, so this part of work I actually did in the in past 3-4 years, and the main idea here is that instead of doing the exact Bayesian posterior, computing that integral exactly, we want to do approximation to that that posterior, and we want to compute these approximation using a particular algorithm that I call Bayesian learning rule. Okay, and what we'll see is that as you change the form of the approximations, you go from like maybe Gaussian to mixture of Gaussians or Bernoulli distribution, to different kind of approximation, you will see different kind of learning algorithms. Okay, so just to make this a little bit more clear visually, I wanted to show you a simple toy visualization. So just think of like posterior distribution that I showed you before. That formula that you compute with Bayes rules, suppose that it looks like this. Okay, so it's kind of a complicated distribution in a 2-dimension in this case. And then I say that I want to approximate that by a circle where I don't change the width. It's like a Gaussian, but only the mean of the Gaussian can be changed. Okay, so this is a very, very simple approximation to a complicated distribution. And if I use this algorithm that I'm going to introduce in the next slide called Bayesian learning rule, then the Bayesian learning rule turns into a gradient descent algorithm. So estimating the mean of the Gaussian comes out to be a first order method. Then if I increase the complexity of this Gaussian approximation to a multivariate Gaussian, where I also estimate the covariance, then if I use Bayesian learning rule, it becomes a second order method, like a Newton's method. So as I increase the complexity of the approximation, it becomes a more complex algorithm in terms of what kind of derivatives it's using. So suppose if I use many Gaussians to closely approximate this distribution, then in that case, we get mixture of Newton's method. Okay, so if you continue like this and you have a very, very flexible approximation that can approximate the posterior distribution exactly, then you will recover Bayes rule. So Bayesian learning rule will become Bayes rule in the limit. Okay, so it's very attractive algorithm in that sense, and I don't really have time to go through the math of this, but I just very quickly want to tell you the principle behind it. And it's about bringing the Bayesian principles in. So in deep learning, you're minimizing this kind of loss. And when you minimize this, you learn only one theta. So you commit to this blue line or red line, right? But what we want to do is we want to learn a distribution over this. So this is kind of an objective that Bayesian learning rule is trying to minimize instead of this other frequentist objective. So here you have a distribution over your model. So this kind of different lines you can sample from this, and you're trying to learn the distribution. So it could be something like an exponential family approximation. So just think of a Gaussian with a mean and a covariance, and you're trying to learn the mean and the covariance. Once you have that, you can use it to sample different lines. Okay. And the main idea is that you want to have this entropy here somehow to keep your distribution be broader. So you want to keep your options open. This entropy helps you to randomize. Okay, but you also want to minimize your loss. So you have this expectation term. Okay, so this is the Bayesian principle. Now, what we're going to do is that instead of using this type of deep learning algorithm which minimizes this loss, we're going to use a different algorithm that's going to minimize this algorithm and this objective. Okay, and I call this Bayesian learning rule. It looks a little bit complicated, but you know, it's just optimizing now the parameter of this distribution. So if you don't know exponential family, it's fine, but it's some kind of parameterization. I'm actually using a specific natural parameterization. You don't really have to know the detail of this. And then I'm taking the gradient of this objective, right? You see, just like this gradient. And I'm taking the gradient with respect to a different parameterization called expectation parameters. And if you don't remember natural and expectation parameter, don't worry about it. What essentially happens is that this kind of gradient is like a natural gradient. So it's not just a simple gradient like this, but it's actually a scaled gradient, like scaled with the Fisher information matrix. Details are less important, but the point is that now you're optimizing the parameter of this distribution with a very specific type of rule. Okay, and what you can show is that once you write this thing and then you choose a form of the distribution, this learning rule turns into a specific type of learning algorithm. Okay, so for example, if you want to recover deep learning algorithm like these kind of algorithm from that update, you choose Q to be a Gaussian, and then you make certain approximation to push this gradient inside the loss, because you want to eventually get the gradients of the loss. Okay. Again, I can't go into the detail, but this is all covered in this draft that we have been writing. If you go to my webpage and you look for this paper, you'll find it. And there is some derivation that's shown, like for example, to get, this is the simplest example. If you want to get gradient descent out of this, you start by choosing an approximation. So you choose this circle, like just the mean is flexible and then covariance set to something fixed. I've just chosen it to be an identity in this case. You write down the natural parameter, expectation parameter just comes out to be the mean in this case. Entropy is constant for this kind of Gaussian. And then you plug, you take the rule, you plug the entropy in, it's constant, so it goes away. Then you plug in the definition of natural parameter, expectation parameter, and then if you look at this and you look at this gradient descent, they look kind of similar already, right? So you see that there's expectation, that's the difference. Then we make some algorithmic approximation. So you push this expectation sort of inside the loss. So you approximate this at the mean. So you're sort of not looking at many options sampled from Q, but rather only looking at the most probable answer, just the mean. So it's kind of a greedy approximation. And if you do that, this algorithm basically becomes same as the gradient descent. Again, the details are less important. What I'm trying to say to you is that Bayesian learning rule, if you choose the distribution properly, becomes an algorithm that that works in practice. Right? So we have a big list of algorithms that we've been working on over the years, and it's all written in this paper. Still evolving, still work in progress. I just told you about gradient descent, but you can derive many different kind of algorithms. There's just two things that you need to change. I hope you can see these small fonts, and I'm sorry if you're seeing this on your cell phone and you can't see this, but there's just, is everything okay, Mark?
Yeah, seems fine. It seems viewable from me.
Good. Yeah. So there's posterior approximation that you have to choose. That's the first choice, and you need to do some kind of algorithmic approximation. So like delta approximation that I just told you. Okay, you can keep changing these approximations, and then you will get different algorithm here. So like SGD, RMS prop, in particular, there's like delta approximation, stochastic approximation, Hessian approximation. There are a bunch of those that you do. And by doing that, you can recover RMS prop or Adam-like algorithm from this update. What we actually showed in our papers, like these two papers, is that if you stop doing some of these approximations, so so if you don't do these approximation, you can design new algorithms. So the details are not that important, but basically kind of remove the delta approximation. Don't do the square root that you do in deep learning. And if you do this, you get new algorithms. And these can then kind of insert Bayesian principle easily without breaking the performance or the code for the deep learning optimizer that you have. So we did this in these papers, like we modified Adam to estimate uncertainty in deep learning, and essentially kind of putting back the expectation with respect to Q, which you removed in the previous example that I showed you. So without going into the detail, I just wanted to show you the visualization of how it looks like. So it's like if you run Adam on this example, you only get like one classifier, it's just like one theta, and you get one line. What Vaughan does is it estimates a Gaussian approximation where you have the mean, which is the red line here, and you have samples from the Gaussian. So you kind of somehow get, keep your options open, and it gives you this flexibility to keep your option open as with the variance of that Gaussian approximation. And we showed that this kind of approximation, even though it gives you this uncertainty, it actually gives very good performance on very large scale. This was published in this paper, and this is all kind of available. The code is available in GitHub, and I'll encourage you to look at that. So, okay, so now we have got to this part where we are showing that we can use the Bayesian learning rule, we can modify Adam, and then we can compute uncertainty with Adam. How good is this uncertainty is the next question. And what I want to convince you now on this kind of continual learning task of why this method actually improves over the existing method. So if you remember, this continual learning was a case where you see part of the data as tasks. So this is on split CFAR, so CFAR 100 data, where the task one is the CFAR 10. So you take first 10 classes and you try to do prediction. You're just training on those, and then you predict. And this y-axis shows you the accuracy, and higher is better here. Okay. And then you continue like seeing 10 more classes at each task, and you do this for a couple of times. Okay, this performance, you can compare what is the best performance that you get is this black line, is that if you had all data at once, then you will get this performance. Now, there are papers, so this paper by Kirkpatrick James from DeepMind, they proposed this method called EWC, which is motivated by some kind of Bayesian philosophy, but it's not really doing any averaging. And that gives you reasonable error. But if you try to do proper Bayesian algorithms, so where you have the distribution and you try to sample from it at every iteration, which is this method called variational continual learning, it actually performs really, really badly. So you see this yellow thing is really bad, okay? And the reason why there's a performance gap is because this algorithm is based on Adam, but this algorithm is based on something that looks very different from Adam. So here you estimate the mean and the variance separately, and that's the reason why you have this gap. So we apply Vaughan on this example problem, and this Vaughan algorithm is just a modification of Adam, so you don't kind of break the performance of Adam, and you don't do much better than existing methods, but you still kind of improve the performance of the Bayesian algorithm. Okay, so what I'm trying to say is that this type of computing uncertainty by changing slightly the code of a deep learning algorithm by inserting this Bayesian principle into it can lead to better performance, although it is not enough. Okay, so in the next part, I'm going to try to convince you that there is another way, rather than just simply approximating the posterior distribution by a Gaussian, there's an alternate way of trying to transfer the knowledge somehow from past data to the future data. And this will be based on this duality representation to do exploration exploitation. So it's very, very intuitive, and that'll be the next part. So I'll stop here and try to see if there are any questions.
Yeah, there's one, and I have my own one to set it up a bit. So okay. You can read the question there from someone about a trade-off between Adam and Voggen. I just wanted to ask a more general question first. People might think that find that choosing an individual line as your fair classifier is easier than maintaining a whole distribution, right? So does Bayesian learning require more data to learn, or how do you overcome that?
So in principle, the Bayesian learning should require less data to learn because it has the ability to adjust as you see data, small data, sequentially, because it tries to fit the data well, but it also tries to model the gap of what you have not seen. I hope that makes sense.
Sure. Yeah, that's how, because it's basically not throwing away as much data, enough information, right?
Exactly. So the issue actually is that there's a lot of things that you don't know. You've only seen a small portion of the data. So you have a really huge amount of uncertainty, and you need to maintain that uncertainty. And there's no particular way for complicated models that you can have a parametric form like Gaussian. For more complex algorithms, you cannot have a Gaussian form. Gaussian form is very, very restricted. So that's why it's computationally infeasible.
And then there is a question there. I don't know if you can see the.
Okay. Is it in the chat or?
There'd be this Q&A box. It's good to see it. It's the first time we've seen questions. So.
Sorry.
I can just read it to you, but.
Yeah, that'll be nice if you could read that.
It says, what is the trade-off between Adam and Voggen? Is it the speed of computation or of the update step?
Yes. So the trade-off is that you have to compute. So there's a Hessian approximation that we do. So in Adam, you are simply computing. I do actually have a slide that let me should be somewhere. Yeah, let me just share my screen again. Screen 2. Do you see my screen?
Yeah, it's coming up. Yeah, you can see it now.
So when you do Adam, you're sort of doing this square of the gradient. Instead of doing that, what we say is that if you want right uncertainty, you should be computing something like this Hessian. And Hessian is hard to compute, so we do a bunch of approximation. So we do diagonal of Hessian, and we replace that by square of gradients, and that requires the computation complexity of this is not too different from this, but the implementation in deep learning optimizer makes it harder. So it runs slightly slower. If you use JAX instead of PyTorch, then there's almost no difference because JAX does some tricks to make that computation easier.
Okay.
So yeah, it's not really a computational complexity thing, but it's rather of an implementation thing.
Okay. Yeah, so there's another question in there, I guess, related to this. Did you see it yet, or?
No, I cannot see it.
You can't see them. Okay. So this question, I don't know if it's from the same person. Current uncertainty estimation methods for deep networks tend to break down for out-of-distribution samples, but humans are very good at recognizing unusual inputs. How could we address this problem for deep learning? Would any of the principles you propose help?
Yes, exactly. So that's a very good question, and that's exactly what I want to talk about. So
let's tie into the next section.
Yeah. Thanks for asking this question. It really kind of lies in this type of, it's a very intuitive thing. So you see that when you say out of distribution, you can see that there are gaps where you haven't observed data, right? But if you do Gaussian approximation, it only can capture so much. So what you are actually doing here is that you're doing Gaussian approximation. So you're at a local, I hope you can see me, you're at a local minima. Yeah, and you have capture uncertainty around that local minima. So this is kind of telling you these different lines of perturbation in that local minima. But there might be some other local minima which you have not captured. So in other words, there are many ways to fail, and you only know, some ways to fail right now, which is around your current solution. So you don't know these other things that you don't know. Okay, and that's how you. And if you don't have this flexibility to adapt to this new thing that you see in the future, you cannot fix these things. So we must think of a new way of solving this problem, and that's basically what I'm trying to get at.
Perfect.
In the next part. Okay, so is that good?
Sure. Yeah, maybe that's a good segue.
So I have now 28 minutes, it looks like, and sorry, I have 18 minutes. Sorry. And I think that's enough. Is it okay if I go till 18 minutes and then we do?
That's probably good. Okay. If people know they have to talk for the hour, but we have the whole slot till 11:30, so the questions in later part of the talk can go past that hour if you like. Yeah.
I'll try to speed it up, but I don't know how this is going to go. Okay, so now, so very good question in the previous for the previous part, and it's really kind of, as I showed that we're doing this Gaussian approximation, and this is very crude way of thinking about, like straightforward way of thinking about uncertainty. So what I want to say to you that we need new ways of being approximate by using Gaussian, for example, but still improving this notion of like not knowing, so like having this uncertainty, trying to fix that in a way. And what I want to tell you is that there is a new view of the problem, and this is through this Bayes duality, looking at a dual representation in the data space that allows us to do this. So I'm going to quickly introduce the concept, and I'm not going to go into the math, but then I will show you an application, and hopefully that gives you an idea of what is, coming. What hopefully is the way that I'm proposing for the future. Okay, so let's switch gear completely and go to a very intuitive question. Okay, so I am asking you a question here that suppose I give you a classification problem. You have one class here and another class here, circles and square, and you have a classifier that you have learned, and it does a pretty good job in classifying the whole data. So your training error is 0. And now I'm asking the question, which data examples are more important for this classifier, right? So I put this red circle here to ask, like, what do you think about this examples versus that example, right? And most of you, when you look at this, you obviously say, well, that one doesn't affect the decision boundary, while this one sits quite close to it. So it looks like that somehow it's holding the decision boundary. If I change these data points, it will affect the decision boundary the most, right? So red circle seems more relevant for the classifier to stay the way that it is. Okay. Now this question is automatically somehow the answer to this question is inbuilt in the Bayesian principle. So what I want to show you is that if you think about the model only looks at this line. So the model view is this, but if you look at the Bayesian posterior, the approximation to it, it gives you an alternate view, and this view is a data view, and this view kind of gives you an alternate story of telling you that the data examples that are close to the decision boundary are the most relevant ones, and they somehow define the decision boundary or support the decision boundary. So this concept is very much like support vector machine, but it comes from the Bayesian principle. So it's sort of an extension of the duality that you have in the SVM, right? So I hope you see the difference between the two views is that the model view is completely ignorant of what the model is doing to the data points. It doesn't pay attention at what data points really define the classifier, while the data view is actually telling you that there is an equivalent representation in the data space, in this dual space, that is telling you that the sensitivity of the classifier is related to removing these data points or adding these data points. Okay, so that defines their importance. So this concept, now I've given you a cartoon picture. Let me tell you how this actually turns out in math. Basically, what happens is that whenever you do a Gaussian approximation, for example, and you try to estimate it using Bayesian learning rule, then somehow you're estimating this dual view of the model. So we showed it in this paper. So this approximate inference turns deep network into Gaussian process. This was published last year, a method called DNN to GP, where we take this kind of neural network. So we have this kind of loss on a neural network, and when we do Gaussian approximation, we show that it gives you an approximation of the loss. So the loss is approximated by the loss of a linear model. So the neural network is now replaced by a linear model, just linear in the parameter, but it's nonlinear in the inputs. So its features are nonlinear, but the model is linear in the parameter. You have some pseudo observations that you come up with and some pseudo noise variance for each data point. The details are really in the paper, but essentially when you read the paper, what you will see, and I don't use the word dual there because it's very complicated to understand it in the dual view, but essentially what happens is that you look at this natural gradient that you have in the Bayesian learning rule, and these natural gradients give you these quantities, okay? So for Gaussian approximation, it's shown in this paper, essentially this guy, this feature, is just the Jacobian of the neural network. So it's the Jacobian with respect to the parameter. And this quantity is defined through residual. This quantity is defined through some second derivative of the loss. The details are in this first paper, but essentially, whenever you do Gaussian approximation, you get this kind of per data approximation of your loss. That is like a linear model. And from linear model, you can go to the dual view, which is in the function space, and in the data space, which is a Gaussian process view. Again, I'm using the word dual, but I'm not explaining to you, and I apologize for that, but this is really a concept that I'm trying to introduce. Now, you can look into the sigma I square, and you could see that if this quantity is really, really large, so the variance is small, then this data point will contribute a lot to the approximation. So you see that I can define like what data points are contributing to most to the approximation, and based on that, I can pick relevant examples. So what we do is that we call these people, these example memorable examples, because these are the most important examples, memorable to the model, to the machine, because if you remove these data points, then somehow the classifier completely changes. Okay, so these dual variables are defining the relevance of the data example. So we use this Bayesian duality to somehow define key points in the data space, and then this will help us to understand the knowledge that's been learned by this classifier. Okay, so that's the overall kind of picture of what you want to think about. And the key point is that why I call this Bayes duality is because you run this Bayesian learning rule where you're computing these natural gradients, and these natural gradients essentially give you dual variables. So we have only written this thing for Gaussian approximation, but this fact holds in general. And we're still working on this paper that should come out in a couple of months, where you'll see that this Bayesian duality is sort of an extension of the duality that exists in SVM, and kernel ridge regression, which only applies to to convex problems, and Bayes duality is trying to extend it to more complicated models like neural network, which already this paper does. So you can see a simpler result that I wrote a paper in 2013 on this convex relaxations of for variational inference, and it sort of connects the two. This paper is actually sort of a generalization of this paper, although when you read it, you don't see it that way. So all of this, I'm sorry that this is not fully published, but I wanted to, in this talk, give you a preview of how these dual variables that you learn using this method can be useful to do continual learning. So before we get into that, let's just go back to the intuition, look into these dual variables. If you use this dual variable, for example, on a neural network trained on MNIST, and you look into the most relevant ones, these are the most memorable examples, you see that they are all kind of weird ones. They are the ones that are hard to classify. As you can see, this one, they're either the ones that lie in the boundary or the ones that are misclassified close to the boundary. So those are the points that are picked here. The ones that are the least memorable, so least relevant, are the ones that are regular shapes. So they all look kind of like normal people. So these are kind of the weird examples, and these are all the normal examples. The same thing you see if you go to CFAR10, then this one are the normal examples that are less important for the model, but these are the ones that are more relevant. So you see here that the scale of this moose or deer is of different focus, while here everything is very regular. You see for horses as well, these are all different kinds that are harder to classify. So I hope that you see the point that it's somehow picking these points as helping us to give us the support points in the data space, in the dual space. And the point is that you can use these examples to do continual learning. So I'm just going to give a brief explanation on that. So before, when I introduced this example, I was telling you that you can use this posterior from this blue line, for example, and when you see the next data point, you can then compute the posterior, update the posterior to get the approximation. Now, the problem here was that if you use the Gaussian approximation here, then it's a very, very simple approximation. Essentially what happens, and this is sort of related to this original paper by DeepMind, eventually when you put this kind of Gaussian approximation, essentially what you are saying, and if you do the math, what essentially comes out to be that it's telling you that the new model that you're going to fit, it should be close to the old model. So you see, it's trying to say, this kind of quadratic penalty, that this red model should be close to the blue model. So it's trying to turn this red line and push it to the blue line. But you see that you have no room here to move. If you move this line towards that, you can miss out on the performance. So this type of simple approximation, the Gaussian approximation, doesn't really do the right job because it's not able to represent uncertainty properly. So the idea with this memorable example using this duality is to instead not look at these parameters. So don't do this. Instead, think about the problem in a new way, that what do we need when we go from blue line to red line? Well, we focus on this part. This is the first set of data. I don't want these predictions to change. So if I define the memorable example, the memorable examples are the ones that are close to the decision boundary. If I change the line from blue to red, and what I want is I don't want these predictions to change. So this is the kind of the idea that we go with. We pick with the dual, we pick the memorable example, then we try to convert this neural network into a Gaussian process, take the linear model, write the dual, and then if XM is the memorable example, we try to make sure that the prediction remains close by. Okay, so I know this looks complicated, but it's essentially an extension of this idea to the function space. We call this functional regularization, but the function space is like this data space where we are looking into the prediction of these points. And then we just want to make sure that when we go from blue line to red line, we don't change the prediction too much. So in that case, this line will be admissible with this new data, the new evidence that you see. Essentially, in this paper we have, so this is, sorry, this is everything okay?
Yeah, that's good.
This is published at NeurIPS now. Sorry, this is an old link, but it's accepted at NeurIPS 2020. And this method is called functional regularization of memorable past, and it's essentially doing what I showed you in the previous slide. It regularizes the function outputs. It's a functional regularization method, and the computation comes out to be very, very simple. You just add that quadratic term in Adam, and the gradient of that is you do a bunch of approximation, and that comes out to be quite simple. So what it looks like is that you start with a problem. So you have, let's say, two classes here, and you have a classifier. Then you identify the memorable example. The classifier might not be very good, so the uncertainty here is not very good, but that doesn't matter. You just try to identify a region where you don't want to lose the information, and then when you get the new data, you learn a new classifier such that these classifications are not changed. So you see that intuitively it makes sense, and then you repeat the process. You find the memorable example, and then you sort of go to the next thing. I hope that this convinces you that this is a new way of thinking about the problem, and that's what essentially happens in this case. So this continual learning example that I showed you previously, where we had this wagon that was doing Gaussian approximation, it was doing quite well, but it was still not hitting. There's a big gap between the performance that we want to be and where it is. If you use this method FROMP, it gives you, quite good performance on these three tasks, although it still has room for improvement because it doesn't do perfectly, but we're still working on this idea. And basically, if we're trying to show that if you throw in more computation, like if you do you compute the dual more accurately, you inject more of the principal. So increase the computation slightly, increase the memorable example, then you are able to match this gap. So somehow improving the cost of the atom slightly, not too much, and still being able to get this performance, it seems very plausible. So this is on MNIST, and this is related to some work from DeepMind that has also come out this year at ICLR. But our method is more intuitive. If you read our paper, there's some explanation there, and it sort of beats these methods too. Okay, hopefully in the second part, I have convinced you that the duality is a useful idea, that you're going into this dual representation, you're fixing some points that are important for you to transfer the knowledge, and then you are somehow regularizing, either preserving the predictions of that space, or trying to somehow correlate this to something that you see in the next step. So this is the key idea that I'm trying to sell, and instead of taking a break for the question, I'll just take the next 5 minutes to close the talk. And let's see, okay, it's already 1. I'm over time, Mark. Yeah,
it's fine. It's a good moment to say, like, you'll wrap up your last part if people have to turn off, but the recording will be online for everyone. But let's just keep going forward, and if we can have some discussion at the end on things, great.
Yes. Okay. So just wanted to close with what I showed in the beginning, like how can we do this type of learning with machine learning algorithms, with machines and with robots and with computers in general. And what I believe is that the aspects that are required for this type of learning, we need to be able to do continual learning or actively selecting the data points, like what my daughter was doing in the previous example, like figure out the preferences of the machine and actively select the data, then do this kind of sequential updating and interact with the environment to do reinforcement learning and learn from other model that we have learned that maybe like with different data sets at different servers in different places, and perhaps do all other advanced things with this. And my belief is that Bayesian principle sits at the center of this because it sort of provides this exploration exploitation trade-off. And I try to put this Bayesian duality as the new way of doing this exploration exploitation trade-off. We're working on these green points that I put there, and hopefully, later in the year and next year, you will see a lot of work from our group on these points. And I just wanted to close with, why do I think that this Bayes duality and the Bayesian principle idea are going to help us to design AI that learns like us? And just to give you very intuitive questions about what we're doing right now in machine learning and why this is not enough. So the first important question whenever you're trying to learn from data is to look at the data and say, what do we know based on that data and the past data that you have? And this is somehow incorporated in the model. So model knows the knowledge that you have. But when you're doing lifelong learning and you have to adjust to the things that are coming in the future, you need to prepare yourself for what you do not know. And this is captured by the uncertainty of the model. But the issue is that this uncertainty is really huge because there are so many things that you don't know in the world. And if you start to model everything that you don't know in the world, it's going to be insane. And this complexity shows up in Bayesian inference, where you see that computing these intervals is extremely hard. Right? So it completely makes sense that this is an insane task. So what I am actually saying is that that's a question that's very, very difficult. It's a good question, but it's a difficult question to ask. So the question that we should be asking is like, it's not that what do we not know, but rather what do we need to know now? So we need to do exploration, but we need to explore at the edge of where we, what we know, at the edge of our knowledge. So this question is very, very important. And that's where I think we should focus rather than focusing on uncertainty. And what I believe and what I've seen in my own research, in my past work, is that posterior approximation is really the key. So I believe that this is how we can solve the problem. So, why I think this, because right now in deep learning, we are focused on like modeling architecture, modeling the loss, and then fitting them well. But model only gives us a representation of the world. So it's kind of says like what things I know my classifier can fit well. So it sort of gives you a representation of the world. But you don't really need to know everything that the model captures, right? When you do approximation on the model, you're actually further approximating the model. So you're doing a representation of the model. So it's actually another layer of approximation. So this posterior approximation somehow can answer this question of uncertainty, right? But if you do it in a naive way, it directly tells you that your approximation needs to be very, very accurate. And that becomes computationally hard. And I think this is where the community is staying, the Bayesian deep learning community, and lots of other Bayesian people in this community are staying in this way. And what I am proposing right now is to say that this is a hard question to ask, but rather we should be focusing on what do we need to know. And I think the Bayesian duality representation that I just talked about here helps us to answer that question. And it's kind of what it says that, if you look at the dual, you're able to have an idea of what knowledge has been learned. So it's a memorable example that I showed you. This is at the boundary of the classifier. But then using this learned knowledge, you can reuse this knowledge in a novel situation. So I showed you in continual learning, you can regularize these memorable examples, and that's how you can go further, right? But then there is a third step that we are taking now, is that you can use these past knowledge that you have in your model And then you can, based on that, you can interact with the environment. You can collect new knowledge, collect new data to improve the knowledge. And this is the next step that needs to be taken. So I'm very confident about that, and I hope that I have given you, motivated you to look into this work. There will be more papers coming out from our group on this topic, hopefully in the next few months, and I hope that some of you will find them useful. So just closing remarks on this. If you want more details on the first part and also on some of the second part, you can see my NeurIPS 2019 tutorial. This was, done in a physical conference. It was very exciting. And for a while, my talk was like the third most popular talk in Slide Lives. And the first one was Benjio's talk, and it had just kind of half number of views that Benjio had. So it's a fun talk. If you want to learn more about the first part, go have a look at that. This paper that I'm writing with my collaborator, Howard Drew from KAUST, is shaping up. It's improving every day. And we're doing second revision now, and it should be available maybe end of this month or something like that. I don't know. I'm very hopeful, but it takes time to finish it. So I will encourage you to look at it. One thing that I wanted to mention is that all of this work actually started in 2016 when I was working with Wu Lin, and I wanted to say this especially because Wu Lin used to be a master's student at the University of Waterloo, which is with you guys, and he has done amazing work, and he's currently a PhD student at UBC and still co-supervised with me and Mark Schmidt from UBC. So this is actually kind of the starting of all the works that I have talked about today. It's hard to parse because it's in a very narrow problem, but I would encourage you to look at that as well. Many people in the past have helped me, and this is kind of like first 2017, 18, I've worked with these people from RIKEN, outside RIKEN, many interns from other places. Recently, we have collaborated with people in Tokyo, interns from all over the world, and these set of people worked on this continual learning and deep learning paper. This one was more on DNN to GP. My colleague Pierre has been a big inspiration for me to think about Bayesian principles, and these other people have helped me as well. So thanks for that. This is the team right now that we have. Many people who are permanent people, although due to COVID, they are still in Europe for some time, for foreseeable future. And we have some part-time students and remote collaborator who were supposed to be here in person, but right now due to coronavirus, they are also not in Tokyo right now. So if you're interested, we have a new web page, and we have some open positions. Have a look at that. And sorry for going over time, but I'm done now.
Great, fantastic. Let's all give Emti a hand. One clap. I need to get some sound of applause. That would help with these things. I'm sure everyone's clapping.
Yeah, I will assume that everybody's.
You just hear it. Boost you up. No, it's a fantastic talk. Thank you so much. We have had a bunch of other questions, so I'll just give some wrap-up kind of things, and then we can kind of keep talking until 11:30 if people want. Especially thanks for staying up so late in Japan time, because he's in Japan. This is like, I'd be asleep by now in his time, but it's great. And really great essential ideas about bringing Bayesian modeling and concepts into machine learning and how it can actually explain some of the stuff that's already happening. My biggest takeaways from your talk are Bayesian posterior calculation is key, dual all the things, and data are people. Because he keeps saying this character, all these people and these people, like that's the letter E or the number 4, but it's fine. Great. So and then so if the other things for people, we have a couple more questions here. Maybe you can see the Q&A box now. I don't know if you can find it.
Yes.
It's off.
Yes.
There are a few we didn't answer yet.
Published or new?
Look under published and scroll down to the bottom for most recent. So if anyone wants to meet with Dr. Khan, tomorrow we're gonna have a slot for grad students at 10 a.m. A few grad students have already signed up. If other people, profs or postdocs on campus want to meet, we could try to arrange that tomorrow morning. And you can also encourage everyone to join the Waterloo AI Microsoft Teams group for people to have more discussions in general, and let you know that there will be one more talk this year. We've been doing pretty good having one every month, so I lost the link. On December 1st, Professor Graham Taylor from University of Guelph will be giving a talk on conditional generative adversarial networks, kind of a high-level view over that and some of his work. And there'll be some more talks every month starting in the new year as well. So, and also, as some people are asking, this talk is recorded, so it'll be on YouTube on our Waterloo AI YouTube channel by the end of the week, and so you can kind of review all the detailed stuff he has there. Great. So, anything in the questions?
Yeah, I think there's a very nice question. What if the memorable examples turn out to be misleading? I don't know if I'm showing up in the live feed because okay.
I can see your
box. That's good.
Yeah, so I don't know. Yeah.
Yeah. So this very nice question actually. What if the memorable examples turn out to be misleading? For example, outliers. Won't this constrain the approach to Bragg prediction? So this is a very good point. And what I actually showed in the talk is that you look into this dual variable and then you pick those dual variable. What I didn't talk about is that there is a nice theoretical result behind this that connects it to outliers and other things. So there's this. It's discussed in our continual learning paper, although we haven't used the method that we should be using. So there is a connection of this memorable pass to leverage score sampling, and essentially, if you go look into leverage score from all classical statistics textbooks and literature, they really talk about this idea that the points they could be points that are misclassified very badly and they are outliers, and the criteria of leverage score somehow is able to differentiate between the two. So if you look into the definition of how you define memorable example, you have two things that you look at. One is like how predictable the example is, and the second is how noisy the example is. So the outliers are example that are not being fit very well with the model, so they are usually excluded from this leverage score. So there are some mechanism in the model to take care of this problem. And of course, in our paper in the continual learning, for deep learning, we didn't compute the exact leverage score because it's computationally infeasible. It again requires you to compute inverses, but there are proxy to take measures against this thing. But this is a good point. And you can, I'm just saying that you can solve this problem by kind of using a matrix inverse of some sort. Should I go to the next question?
Yeah, go ahead. Yeah, I don't know. I was trying to see.
There was another question. Yeah, that says, did you try the Franck method on long learning sequences? Memorable examples were stored for each class. So yeah, this is also a good question. So we have not really tried too long. So we have tried it on, I think it's like 11 tasks or something for C4 100, or something like that. We haven't really tried too long sequences. We're actually trying to work on right now applying this to that kind of problem. So something like ImageNet. So something should come out soon where you will see this. You're right that memorable examples are stored for each class, and they grow in size with time. And this is, again, another trade-off that one need to do is to keep pruning the things that you've seen in the past. Hopefully, as you see more data, then you kind of have a better idea of what you should be preserving. You could look into the correlation between these examples. So For example, you can compute these kernel matrices that we get, and you can use that to prune the example. So there are mechanisms to do this. We've really just kind of started with this, so we haven't really done. But that's a great question. There in the new question, there are.
Yeah, those are all just fine. That was just a discussion with people who asked the questions already.
Okay, I see. Yeah. So there's no new questions, I think.
Not that I see, yeah. What did I have? I had a broader one, since you have a little bit of time. Just talking about, it seems like you mentioned how using your dual approach like generalizes or matches the SVM kind of approach of these, anchor points to explain the model. Is it a broader thing that using Bayesian and dual approaches always generalizes that concept? Or are you just trying to bring back all the machine learning away from neural networks and have SVMs beefed up with Bayesian? Can it beat them again, or trying to restart the war?
No. This is kind of like it's bringing back the idea in the sense that when we think about SVM, I mean that was a great idea, right? That you have a sparse kind of support. So you define these dual variables that has for each data example you have a variable, and then some of them go to 0, and that says you shouldn't pay attention to those data points at all. But then for this you need to be able to have a convex problem where you can write the dual and then you solve the dual problem. And what I'm trying to say is that if you define the posterior approximation like Gaussian, and then you use this Bayesian learning rule, it actually, you can recover this dual result from that. And I'm making a statement right now for which you don't have the proof, but I do. So this will be published at some point. Yeah. Yes. So it's kind of it's kind of this reduction thing that I did in the first part of the talk, where you say if you make certain approximation, the algorithm becomes like the algorithm that you know. Like if you want to make it to be Newton's method, you can do it by making certain approximations. So it's again the same, because the Bayesian learning rule reduces to these algorithms, you can actually recover these existing framework by making these approximations. That's the key idea.
Yeah.
So that's how it's kind of extensive. It doesn't solve the problem. It doesn't make the problems convex,
Right.
But it's trying to. So once you converge to a local minima, it's sort of looking into the dual around that, right? So it's again it's like going into. So you can still write the dual at the minima. You can write the KKT conditions, and those KKT conditions have the dual variable for each loss, for data example. And you can read these dual variables from there. So you're not really doing SVM-like computation. You're still running Atom. But in the end, when you converge, you invoke the principle to compute these dual variables.
Okay, so it's something that you can always get out these variables that have an interpretation, which you can explain because we're familiar with SVM, and this could apply to other areas. So extracting some interpretable numbers, potentially interpretable numbers out of a lot of these models is a big idea, right?
Exactly. Yeah, it is a big idea. So I think this is a big idea. Although, when we wrote the paper, it's hard for people to see this right now. This is why I'm giving this talk.
Mm-hmm.
But over time, you see that the math becomes clear. This is all kind of well thought through to show that the natural gradients that we have in the Bayesian learning rule give you these dual variable is the general thing.
Yeah.
How useful they are in practice is something that you need, we all need to work on this.
Of course, that'll be always the next step. Yeah. We have another question came up replying to that discussion, so I'll just publish that. Maybe that'll be our last thing. Examples that are not memorable could become so with new observations, but they would have not been memorized. This seems like a fundamental limitation.
Right. So so all of these things are. So Should we read the question again, or can I
go ahead? You can read it. Yeah. I don't know if anyone can see it. It's from Professor Sarnecki. Now it's showing the name somehow. I don't know how that's happened. He's in the EC department of Waterloo. Yeah.
Yeah. So this is a great question. The question says examples that are not memorable could become so with new observations. but they would not have been memorized because they were in the past. So this seems like a fundamental limitation, which I completely agree with the point. It's actually again and again pointing that there's no easy solution to this thing, right? Things that were not relevant in the past could become relevant in the future. And so, you know, for us as well, like some important information that we learned when we were kids, and we actually forget them, you know, and we need to really relearn this. And somehow we can't figure this out, that some things are missing in my, you know, in the new data that I'm seeing, and I need to relearn this. So what the dual variable and this memorable example, this concept is giving you is not that it's telling you that it will solve the problem completely. Rather, it is giving you a handle on how to go back and maybe carry things and relearn them, the things that you actually didn't learn properly. So suppose new data points that are coming in and that are telling you that, oh, I'm not able to classify them well, I think I need to update my memorable examples now. So I need more data points now. I need to see these classes again to be able to adjust. And with this kind of dual approach, what you can do is you can correlate new experience to your old experiences. You're able to directly say, you know, what you're good at and what you're not good at. And this is not possible if you look into the model parameter. So my point is that the parameter view, the model view, does not give you these tools to be able to look into the future, relate your past to the future, and then choose a future so that you can, you know, make up for the mistakes that you have done in the past. And these are the three things that I had in my you know, last conclusion slide, and that you need to intervene with the world and have query questions to be able to improve your knowledge. So you're right that this is a limitation in the current thing, but the framework allows for fixing these issues.
Great. So
there's no feedback. I don't know if I answered
his question. Yeah, well, maybe have a meeting with him and talk about that further. So let's leave it there. I think it's a good place to wrap up. Thanks again, MT, for staying up late and a fantastic talk. And hopefully we can all kind of keep talking in the future and do all the things and make our methods better.
Right.
Okay.
Thank you very much.
Thank you, everyone attending. I put in the next things. We'll see you December 1st for our last talk of the year. And stay safe and healthy, everyone.
Yeah. Thank you for having me.